If a non-conservative force like friction acts on the system is going to lose energy. For example, in the form of thermal energy. So in that case, mechanical energy will not be conserved. So while solving questions, we need to be careful about the presence or absence of non-conservative forces. So again, consider we have a block which is kept on an inclined plane and it is sliding down this incline and finally reaching the bottom of the incline at the final velocity v. So according to the law of conservation of mechanical energy, initial energy will be equal to the final energy. But do remember, you have to apply this equation only if friction is absent. So let's see, use mechanical, remember this as a rule. So use mechanical energy conservation only if conservative forces are present. If non-conservative forces are present, for example, friction, in those cases, the approach is a little tricky to apply. But in most cases, we can consider this as a rule. So mechanical energy conservation applicable only if conservative forces are present. Now imagine if this inclined plane surface is rough, so it has friction. So if the surface is rough and has friction, it is better not to apply the energy conservation. As I explained earlier, it is a little tricky to apply it. The easier way out is to use the work energy principle. So for the rough surfaces, it is better to use the work energy principle. Now let us understand this by taking a specific example of a ball bouncing off the ground. So imagine there is a ball kept at a height h above the ground and it is released from rest. So as we release the ball is going to fall down towards the ground. And let's say we label the topmost point as A and the point where the ball hits the ground, that is point B. Now, when the ball hits the ground, it is going to bounce back up. And of course, after the bounce, the ball is going to follow the same line and it is going to go up. But just for the sake of clarity, we will draw a separate line for after the bounce. So after the bounce, let's say the ball is going up and it reaches the highest point. And let's say that point is labeled as point C. So just to clarify, we have drawn two separate lines. The first dotted line is for when the ball is falling down, and the second dotted line is for the ball when it is going up. We have drawn separate lines just for the sake of understanding. Please note that the ball is going to go down and bouncing back up within the same straight line. So to sum up, the situation which we are considering here is a ball is released from point A, it rebounds on the ground at point B, and then it goes up from B up till the maximum height C. So now we have to consider, is the law of mechanical energy conservation applicable here or not? So how do we analyze it? So we need to observe the different forces acting on the object. Remember the concept, if conservative forces are acting, then we can apply the mechanical energy conservation very easily. If we have a non-conservative force present, then mechanical energy conservation cannot be applied. So over here, the ball is going to bounce at the point B. At the point B, ground pushes the ball back up with a normal reaction force. Let us understand this point in a little more detail. So imagine we have the ball, it is coming towards the ground. The moment it hits the ground, so we are considering the point B when the ball has made an impact with the ground. So over here, I have drawn the ball and the ground separately just to draw the separate free body diagrams for the ball and the ground. So let me repeat, the situation which we are considering is when the ball is hitting the ground. So the ball is in contact with the ground. And over here, we are drawing the separate free body diagrams of the ball and the ground when the ball and the ground are in contact with each other. So what are the different forces acting on the ball? The first force is the weight of the object, which is acting downwards mg. Now let us summarize the situation. We had a ball which was released from rest. It is going to speed up. It is going to hit the ground at the point B. Now, since the ball is hitting the ground, which means the ball is providing a force to the ground in the downward direction, which we can show over here. So this N is the normal reaction, or rather the force provided by the ball to the ground in the downward direction. And according to the Newton's third law, if you remember, forces are always in pair. So if the ball is pushing the ground downwards, so the ground will also push the ball upwards. And according to the Newton's third law, the magnitude of those two forces will be the same, direction is opposite, and forces always act on different objects. So one force is acting on the ball, the other force completing the pair is acting on the ground. So we conclude that the ball is being acted upon by a force which is the normal reaction. Now, normal reaction is a non-conservative force, and we already know the principle that we can use the mechanical energy conservation easily if only conservative forces are present. Now, since we have a non-conservative force, so mechanical energy cannot be conserved. So let us summarize. Consider all these points. If the object is going from A to B, or the object is going from B to C, or we consider the entire motion starting from A all the way till the final point. So in these motion, we cannot apply mechanical energy conservation because of the presence of normal reaction, as it is a non-conservative force. But there is a trick which we can use to apply the mechanical energy conservation in such cases where the ball is bouncing off the ground. How do we do that? So look at the same diagram. So the ball was released from rest at the point A. It falls towards the ground. It is going to speed up, but just before hitting the ground, let us draw the position of the ball. So let's say the ball is at point P when it is just about to hit the ground. So P is the point just before impact with the ground. Afterwards, the ball is going to collide with the ground at the point B, and just after the bounce, we can draw the position of the ball over here at the point Q. So Q is the point just after impact with the ground. And we can also see the direction of velocities at the point P and Q. So just before impact with the ground, the ball is moving downward, and just after impact with the ground, the ball is going upwards. And now if we consider these points, we consider the motion of the ball from A to the point P. P is the point just before impact with the ground, and consider the motion of the ball from Q to C, which means just after impact with the ground until it reaches the maximum height C. So when the ball is doing motion from A to P or Q to C, only the gravitational force is acting on the object. So mechanical energy will be conserved, as gravitational force is the conservative force. And using the law of mechanical energy conservation, now we can write that the total energy of the ball at the point A will be equal to the total energy of the ball at the point B. Similarly, the energy of the ball at Q will be equal to energy of the ball at C. But total energy of the ball at A cannot be equal to total energy of the ball at C. So EA is not equal to EC. And why they are not equal? Because if we are considering the motion of the ball from A to C, the ball is going to hit the ground, because of which the ground is going to provide an upward normal reaction to the ball, and normal reaction is a non-conservative force, and that is why EA and EC are not equal. And let us summarize the entire situation. Whenever the ball is bouncing off the ground, so from A to P or from Q to C, we can apply the mechanical energy conservation like we have shown here. But if you consider the overall motion from A to C or A to B or B to C, so considering all these motion types, mechanical energy will not be conserved, because in these motions, the ground comes into the picture and the ground gives a normal reaction to the ball in the upward direction. Normal reaction is a non-conservative force, hence the mechanical energy is not conserved. Now let us solve a question based on this. So a squash ball is released from rest at a height h above the ground. So let's draw a diagram. We have a squash ball which is at a height h above the ground. Let's draw the diagram. And it is mentioned that at each bounce, 75% of its kinetic energy is lost to the surroundings. We need to find what is the height reached by the ball after its second bounce. So how do you approach such questions? First of all, let's draw a diagram, and let me label A is the original position of the ball when it was at a height of h above the ground. So when it is released from rest, initial speed is equal to 0, and then the ball starts to travel downwards. Eventually it is going to hit the ground, let's say at the point B, and then it goes back up until it reaches another maximum height. Now, this height will not be equal to the original height because the kinetic energy is lost to surroundings. And let's say this height is h dash. So this is the height of the ball after the first bounce. Now, the question was to find the height after the second bounce. So let us try to find h dash first. And how do we do that? Using the law of mechanical energy conservation. But there is a catch. Remember, mechanical energy is conserved only when conservative forces are present. So till the time the object, the ball, is only under the influence of the gravitational force, we can apply the law of mechanical energy conservation. But notice, when the ball makes an impact with the ground will provide an impulsive normal reaction to the ball. And just to clarify, let me draw a diagram. Let's say the ball impacts the ground. So the ground will give a normal reaction in the upward direction. Now, normal reaction is a non-conservative force. So mechanical energy conservation will not be applied if we are considering this normal reaction. Now, to tackle that issue, what we will do instead of B, which is the impact point with the ground, we are going to consider a point just above B. Let's call that as point C. So C is the position of the ball just before hitting the ground. And let's say the speed of the ball at that point is, let's say, V. So let me repeat. V is the speed of the ball just before hitting the ground. So from A to C, we can consider